Now I'm going to be recording this and posting this, so if you if you want to put something, you can put something in the chat window is fine. If you want to ask a question, if you want to unmute yourself and ask a question, your voice will be recorded and posted out onto YouTube. So just want you to be aware of that. And so if you don't want your voice out on YouTube, then, just put it in the chat window there. Okay, so we're talking about the ControlLogix PLC. Now, I believe when you took PLC 1, you guys just used the CompactLogix PLC. And there's a lot of similarities, but the CompactLogix, just by the name, right, it's kind of a smaller sized PLC. So it's not quite as expandable. But they're really nice PLCs, and of course they're probably a little bit cheaper because they're just kind of on the smaller side. All right, so the ControlLogix are much more expandable. So when you look at them, when you look at the different PLCs, you see like this one here has power supply. So this large section here on the left side, that's actually just a power supply for it. So it's, Allen Bradley's official power supply for the ControlLogix chassis. And then there's various I/O cards and of course a PLC processor in there. All right, so before we quite get into that, I just kind of want to go back and when we look at Allen Bradley's older style PLCs, one of them was called the MicroLogix, and there's a lot of these around. These were fixed I/O. The MicroLogix just had a fixed amount of I/O. So there was like the MicroLogix 1000 that had just 10 digital I/O. Or 16 I/O or 25 I/O, but that was it. Whichever one of those models that you bought, that's all the I/O that you had with it, and you couldn't add any more to it. Okay, so it was kind of fixed. And the other thing is, like, they actually used a rack slot sort of address spacing on them. Okay, and the MicroLogix were just like rack 0 because they you couldn't add a rack to those. Okay, but so those were there. The Slick 500, okay, SLC 500s, a lot of times people called that the Slick 500, and I don't know what happened to my image up there, but those processors were kind of like the core Allen Bradley before they moved to the ControlLogix model, but they also used a like a slot referencing. Okay, and then the PLC5 was a really old style. They used a rack and slot address spacing. Okay, but some of these are still in use. Okay, these were actually, I guess, the PLC5 model was late 80s, early 90s kind of time frame when they were new. But once you put something in place and it's working and it's making money, you don't change it, right? You don't change a production line just because somebody made a brand new PLC. Okay, if the line's still running and it's still making money, you're not going to shut it down, and because anytime you shut down the line, now you're losing money you could be making. So there are a few of these still around and still in production. Okay. Now the CompactLogix, which you used in PLC1, and along with the ControlLogix, we're going to also work a little bit with this semester. These use what's called tag-based. So you create a tag, and you assign that tag to the IO on there. All right, and so these are expandable. Okay, so you can add modules to them, and of course we have 2 modules on the ones that we have in the classroom. All right, the ControlLogix, okay, they use they use a chassis called the 1756 chassis. The CompactLogix use a 1679 chassis, but the ControlLogix use a 1756 chassis. So this is the 1756 chassis here. This is one we had in the classroom, and you can see there I kind of labeled the PLC, and then there's actually 4 slots that don't have anything in them. So next to the PLC there, we actually had 4 slots with nothing in them, and then there were some more slots there, and so this was actually a 17 slot chassis. Okay, so when you do the ControlLogix, they come in different size chassis. I think I say that somewhere on here. We'll get to that, but they could do 4 slot, 7 slot, 10 slot, I think like 14 slot or 17 slot chassis. All right. Where like the CompactLogix that we have in the classroom, you can only add, I think, 3 modules. We have 2 added, but I think they can only handle like 3 modules. Now, some of the other models of CompactLogix can handle more, but but they certainly can't go all the way up to 17. All right, so now when we communicate with these, of course, we're going to be using our standard Ethernet cables. And so we talked about those in the last lecture. Those, we talked about if you're plugging from a laptop, say, directly into the PLC, you need to use a crossover cable, which would have a 568A on one end and a 568B on the other. But if you're plugging the PLC into a switch and you're plugging the PC into a switch, then the switch basically does the crossover for you. So you would just use straight through cables. So you'd either have a 568A on both sides or a 568B on both sides. That would be a straight through. And again, the switch does the crossover for you. That's one of the things that it'll do. All right, so to connect to the ControlLogix, and this is kind of a refresher because it's really pretty much the same thing that you do whether you're connecting to a CompactLogix or a ControlLogix. So when you open up the software here, let me see if I can do this. If you open up Rslogix #1, okay, so since we're connecting across the Ethernet, okay, there's 1 of 2 drivers we could use. One of them is called Ethernet IP for that industrial protocol we talked about in the last lecture. And you can do that. If you're on the same network, it works really well. But our PCs are not on the same network that our PLCs are on. So what we want to do is we go to Communications, Configure Driver, and then we're going to choose Ethernet device, not Ethernet IP. Okay, Ethernet IP works really quick if you're on the exact same network, and then all the devices on that network just pop up. It just kind of, they would all appear, which is really nice. But for us, we're going to create an Ethernet device. I like to label mine the PLC network, okay, because that's where the PLCs are at. And so if you look right now, you can see we have several of these are on here. Now to configure this driver, you come over here and say configure driver, and you can list all of the IPs in one shot. So see, what I did was I did this ahead of time, and I just went in here and added the IP of all of the CompactLogix PLCs and all of the ControlLogix PLCs, and I even have some other devices listed here. All right, and so you can see these guys are just showing up here. And so the ones that are green, these guys are actually plugged in. And the ones that are red, they're not plugged in or powered on, or they're not on this network, one of the three. Okay, so you can actually see here that I actually have this 150 is plugged in. Okay, so this is a CompactLogix PLC, right? We can see that by looking at the back plane. Remember, I just said it's a 1769. That is the chassis of the CompactLogix model of PLCs. They use so the 1769 is a chassis. And then what's nice about the Rslogix software here is the fact that you can see what inputs and outputs are available. Okay, so you can see here that, you know, there's just the local bus adapter, but then there's 16 high-speed 24-volt DC inputs, and these are embedded into it. So we can't actually remove this. It's not a module that can be added or removed. It's embedded in there. Okay, but it's classified as module 1. And then there's a second module which has 24 DC outputs, which are sourcing outputs. If you remember from PLC 1, we talked about if you have a sourcing output, you're going to be outputting to a device, the device needs to be a syncing device. If you have a syncing output, then you need to have the device you're connecting it to must then be a source voltage. Okay. And then we have here, and the same for the inputs, you need to have either syncing or sourcing. But you notice this one doesn't say syncing or sourcing, and the reason for that is you get to choose that when you wire it up. So when you wire up these inputs, you can wire them up as sourcing inputs, and then you would have to wire them into a syncing sensor. Or if you have sourcing sensors, then you would have to wire them up so that your PLC was a syncing device. Okay, so that's why it doesn't say source or sync on the inputs, because it's your choice based on how you wired the device up. Now, we've already pre-wired them to the terminal blocks, and off the top of my head, I don't remember how we wired them. I'd have to look. Okay, so but you know, but it's how you choose to wire it for the inputs. But the outputs here are sourcing, so they don't give you a choice on how to wire it. It must, you know, we are going to source the 24 volts out to whatever device that we're going to drive. So the device must be a syncing device for outputs. All right, and then of course we have our relays, which is a extra module that we've added. And then we have our analog card. Now this is, again, this is the 1769 CompactLogix. But if we come over here to 164, this is a 1756, which means it's a ControlLogix chassis. So it's a ControlLogix chassis. It has a L55 PLC plugged into it. Okay, so that's the model number of the PLC, which is a Logix 5555. Okay, so that's a ControlLogix PLC, and that's plugged into slot 0 of the 7 slots. So this is a 7-slot device, but we start counting at 0. Okay, so the PLC is plugged into slot 0, and then we have our Ethernet card plugged into slot 1, and then we have an analog input on slot 2, and an analog output, which is a current. You see that OF6C Okay, the O means output. So like here on slot 2, we see I means input. Okay, and there's 16 inputs on this. Okay, so you see IF16. I'm not sure what the F stands for. Somebody knows what that stands for? Go ahead and put in there. Okay. All right, and then you see so you see the O means output, and it's got 6 outputs, and they're current outputs. You see the C there means current. All right, and so by reading the model number, you can at least tell some information about what's going on, like how many you have. So we got 16 inputs, and we got 6 current outputs. Okay, what that means, what does a current output mean? That means that's at 4 to 20 milliamp, or you can configure it for a 0 to 20 milliamp if you want. Okay, but that is the current output setting there. So that's that analog signal, that 0 to 20 or 4 to 20 milliamp current signals that we've been talking about a lot. All right, so now this device here is an input device because it's got an I. It's got 16 inputs, okay, and I'm not sure what the B stands for. It might stand for binary, but I'm not 100% sure on that, but it makes sense because this is a DC input card, okay, and then this is a DC output card. And then we also have the OW16 relay card. Now, what I want to point out to you here as I look at this, this is an OW16. And if we come up here, back and look at this guy, he had an OW16. I guess it didn't actually say OW16 there, but it is actually an OW16 relay card. But this one here is a 1769 module, so it won't plug into the ControlLogix. It plugs into a CompactLogix. Where this is they're actually the exact same model as far as the circuitry and stuff, because they're both OW16s, but the way they plug in, right? This one plugs into the 1756 ControlLogix chassis. All right, and so even though they both have 16 relays, all right, and so they're effectively identical as far as what they do and everything, but they're designed to plug into a different chassis. All right, so we can see that again. We can see that in this Rslink software. All right, and it's very helpful because when you go into the Rslogix 5000 software, so when you go into the Rslogix 5000 software, okay, and okay, good, it activated this time. Last time I opened it, I wasn't connected to the network and it was giving me an error, but so anyhow, when you open up the Rslogix and you create a new program, see the difference is this is our communication tool. So this sets up the communication between our PC and the PLCs, okay? Rslogix 5000, on the other hand, is programming software. And so if I come over here and say, I'm going to create a new program, now I have to decide what controller am I going to write to, okay? And so if I want to go to the L55, which is the ControlLogix, then you choose that. Now, if you do that, you notice we have currently installed 3 revisions, but 19 and 20 are grayed out. I can't select those, okay? Because the ControlLogix don't use those revisions. And so if you have to install the software on your laptop or your desktop computer and you're trying to install Rslogix 5000, you need to know which revision or revisions you're going to be using. Okay, so our ControlLogix controllers, okay, they're actually a little bit on the older side, and they only use version 16. Now, they do have newer ControlLogix controllers out there. We just don't have them in the classroom. So the ones that we have in the classroom only work with revision 16. Okay, that's the L55. We actually also, one of our ControlLogix is an L61. So it's a little bit newer than the 55, but it still uses revision 16. All right, and then we would create a name for this. A, B, C, D. Not sure what name to create here. I'll just call it ControlLogix example. Okay, and then you can put in a description. It's a really good idea to put in description here of what your program is for. But this is what I wanted to show you here. See, here are your different choices. So you can get a 1756 4 slot, 7 slot, 10 slot, 13. I think I said 14. It's a 13 slot and a 17 slot. They also have kind of a special one, which is called the XT chassis that you could purchase. Now, in the classroom, currently, we used to have all 17 slots, but as you saw from that one picture, we weren't using half of the slots. And so we actually ended up going ahead and getting 7 slot chassis. So we have 7 slot chassis, and we have one that's a 10 slot chassis. So you have to look at the one that you have and see which slot it is. Now, you can either obviously look at the chassis, look at the PLC and count, or you can also look at Rslogix, because Rslogix is already communicating with it. And so I can clearly see here, I've got 6 slots. Okay, or well, excuse me, I got 7 slots. So I got the PLC in slot 0, and then I got 6 more slots. So I'm using the 7 slot chassis. So I'm going to choose the 7 slot chassis here. And then I need to know, where is the PLC? Is the PLC in slot 0, slot 1, slot 2? You got to know that. All right. I mean, again, you can look at Rslogix or look at the actual PLC and figure that out. Okay. It's visible. Okay. But when you put it in here, you need to tell it, hey, my PLC is in slot 1 or slot 0. Okay, in the classroom, they should all be class 0. And then you can decide where to put your files. Now, it likes to put it on the C drive. Do not put files, programs on the C drive. You will lose them, right? Because they reboot those computers at midnight every day, and anything on the C drive is wiped. So make sure you put it on the D drive or some other drive, okay? For me, I'm actually using a laptop right now. I'm not in the classroom. So I can put it in here in the users, or I could browse. You could put it on a flash drive if you wanted. Okay, and I'll just put it in here and create that. All right, so I think these slides just pretty much show you what I just showed you in Rslogix here. Let me see if I left anything out. Okay, so yeah, so when you create names, okay, try to be descriptive and say, what is this? So lab 1 is like analog signals. Don't just call it lab 1 or test 1. Those are just horrible, horrible names. And you need to make it descriptive so that you have an idea of what it is. So when you come back later, if you decide you want to open it, you have a better idea before you waste time opening it. All right, so while that was going there then, not sure why it's bleeping at me here. Okay, so here it's opened up now. Rslogix has opened up, and it's got the controller here. Now notice when you come up to the very top of this tree here, you can go to properties and you can see the controller that you selected, and you can change that. So if you selected the wrong one, you can change your controller. And or if you chose the wrong chassis, you can change it. Okay, or if you got the controller in the wrong slot, you can change that also. Okay, so so you can change these after the fact. The other thing is that you come over here, you see faults. So one way to get a guaranteed fault would be that if you selected under general, if you selected, the 4 slot or the 13 slot chassis or something like that, and you only have the 7 slot, and then you try to download it, it's going to fault. So what do? You come over here to fault, and it'll show you some information about the fault, and then you click on clear major faults, okay, and clear that fault. If you don't clear your fault, that PLC is not going to work, okay. And so if your PLC, and there'll be a little red light on the PLC indicating fault, okay, you must clear that for it, before you can do anything else with that PLC. So you have to, come over here and go online, and then when you're online, then you can clear the fault. See, right now it's grayed out because I'm not online, and so I can do that. Another way to get a guaranteed fault would be to add a module. So remember down here in IO configuration, we can add our new modules. So like I can come over here and I can go to my digital modules and choose that 1756 OW16, which I showed you we have installed. You can add that. Okay, and when I add that, okay, it's going to ask me what slot to put it in. And if I put it in the slot and it's the wrong slot, that's another guaranteed fault. Okay, so you need to make sure that you select the right slot. How do I find the correct slot? Again, we flip back to Rslogix, and I look and see where's my OW16. It's in slot 6. Okay, so I come over here and I set this to slot 6. Okay, and this is a relay module, so I can come in here and type in relay. Now, one other thing, please make note of this. Okay, so, if you got a piece of paper or something handy, make a note of this so that when you're in lab, when you are doing the ControlLogix PLC lab, you must disable keying. Okay, you must disable keying on here. I actually think, I haven't tested this, but I think the problem is if you look at this, it says revision 3. So these IO modules, here, they have like a firmware in them. And if the revision doesn't match, then you will get an error. Now, again, if you come over here to Rslogix and you do a right click on this and you go to device properties, it will tell you that, see, this is revision 2. Okay, so it's major revision 2, minor revision 1. All right, and so, but when I selected this, it's at revision 3 and 1. I'm just going to cancel this a moment and re-add it. Okay, so a right click on IO config, new module, and then I'm going to, relay modules are OW16, they're digital modules, so I'm going to look under the digital, and I'm going to say okay here. And see, now actually I could have selected the revision here and made it revision 2. And if that's okay, then I probably don't have to disable keying. All right, but if you select the wrong revision, you can still get it to work if you disable the keying. Okay? And it'll work fine for our purposes. And remember, that is slot 6. Okay, and so this is my relay module with 16 relays. Okay, and so we can then add that. Okay, and there's not a whole lot of configuration here. Normally we don't have to mess with this module. Okay. All right, but if we wanted to add an analog card, okay, so we're going to add an analog card. So let's go back to Rslogix, okay, and we see, I already pointed out, slot 2 has an IF16 card, okay. And again, if we do a right click on this and look at device properties, we can see it's actually only revision 1 on there. So it's revision 1, minor revision 5. So if I come over here and I'm going to say new module, and I'm going to look for an analog card. So I'm going to expand the analog, and I want IF16. Okay. And so this is going to be analog input, and it's in slot 2, and it's revision 1, minor revision 5. So if I take the time to select those, then I probably don't have to worry about disable keying. Okay, but I've never actually tried that. But if you're having any problems, make sure you just disable keying and you'll be fine. Now, the other thing I want to point out about this analog module is we talked about inputs and outputs. We talked about binary numbers last week. And if you choose integer data, then it's going to convert the data as simply integers. But if you choose floating point values, it will actually allow you to kind of scale it on the fly, which is kind of nice about the ControlLogix. The analog or the CompactLogix will not let you do that. Okay, so these give you a lot more choices with how you have it. So if you can select either input mode or differential mode. Okay, and I'll come back to those in those slides in a little while. Okay, so I'm just going to cancel that for right now. But that's how we add inputs and outputs to our PLC. And the reason we have to add them here, see, like if you look at Rslogix, you're like, Rslogix knows what I have. You're like, oh, Rslogix knows what I have. No problem, right? It knows that the PLC is in slot 0 and the Ethernet is in slot 1 and the analog input is in slot 2 and the analog output is in. It knows this because the Rslogix is talking to the PLC. But at this point in Rslogix 5000, we're not actually talking to a PLC. Okay. So if we come over here and click on the who's active, it looks like a little network thing. Okay. And then we can browse our PLC network and we can connect to that PLC. Okay. And so we want to drill down. You need to talk to the PLC. You see how everything over here on the right is grayed, right? Upload and download, go online and update firmware. Those are all grayed out because I haven't got to the PLC. When I choose slot 0, now it knows that I'm actually communicating with an actual PLC. And so I select this, I select the actual PLC, and then I can download my program. Now at this point, I actually haven't created a program, so it's a null program. Now I want to make a point here. The newer PLCs on this software, on the newer PLCs, you don't actually drill all the way down to the PLC. You just choose the main IP here and you're good. Okay, so it depends on which model you're working with. If you're working with the ones that we currently have in the classroom, you have to drill down to the PLC. But if you're working, if you're watching this video and you actually have a newer version of the PLC, you just select the IP address and then you would be able to good to go. But so I need to do that, and I'm just going to download this program. Now again, it's a null program. There's absolutely nothing in this program, but it'll connect me and let me go online. So I just allow the download. Now download means that you're taking the program from your PC or your laptop and you're putting it into the PLC. Upload means you're taking it, whatever program was currently in the PLC, you're going to bring it up and be able to view it and modify it in the PC or the laptop that you're communicating with. All right. Now, the other thing to notice is over here, it says remote program. It's kind of a cyan color. So I downloaded the program, but my PLC is in program mode. So that means it's not actually running. It's just sitting there. And so if I want to run it, I click on this little down arrow here at the cyan color and come over to run. And then I can change it to run, and it says remote run, meaning that I executed it remotely. And then you can see that it has turned green here. And so the PLC is actually running the program. Now again, if we come look at my program, there's nothing there. It's actually not running anything. Okay, there's no code there to run, but it's online, and I can actually go back to program mode if I want now. And that, if it was running a program and you switch it back to program mode, then that will stop it from executing any program that it might have been executing. All right, now that I'm online though, I'm still online communicating. I want to just pop back up here to the controller configuration and just show you that now I can't change the slot or the chassis because I'm actually live online. But if I come over here to major faults, if I had a major fault, I could clear it. Okay, and if I had a minor fault, which actually I do have a minor fault, which is because my battery is dead. Okay, so the PLCs actually have these batteries in them so that, if they lose power, they won't forget whatever program you just downloaded to them. All right, and so you can see that I do have a battery fault on these. All right, we don't worry about it in the classroom because, we're just going to be downloading a new program anyhow. So it doesn't matter whether they remember it when you shut it off. One of these days, I do hope to update the batteries, but we just haven't made it a high priority. So anyhow, if we click on clear errors that are faults, that minor clear minors, that's going to clear the minor error. And so you saw it disappeared, but of course it came right back because the battery is still dead. Okay, so we actually need to put in a good battery, and then we would come over here and clear that error. You can also, set the date and time on the PLC and set some other configuration in here. Now, it doesn't do us any good to do that because the battery's dead. So once you unplug it, time would be lost anyhow. But once we get our batteries corrected, then we can come in here and we can actually set the date and time for the PLC and run that. All right. So that's just kind of some general configuration for the ControlLogix. Again, it's practically identical to what you were doing for the CompactLogix, but there are a little bit of differences as far as your modules. You have to add all the modules because you don't have any embedded modules. Okay. And let's see. Now, some of the newer ones, I don't think these guys do it, but some of the newer PLCs, once you connect to them and you go online, they will actually be able to then pull in all the modules that you have. Okay. Because they, once you connect it. So version 16 doesn't do that, but I believe version 20 does. I'm going to go ahead and connect to the CompactLogix. And so I'm going to come over here now, and I'm going to go to the CompactLogix 1769. Okay. And the one that we have is the L23EQB1. And I'm going to select version 20 for that because that's the version of firmware that they are set to. Okay, so you need to make sure you match that. And so this is just going to be the CompactLogix. And so, it's going to kind of create the program here. And then once it comes up, I'm going to connect to the CompactLogix I have turned on. And I'm going to see if it can pick up the I/O. I'm pretty sure that version 20 would grab the I/O. I definitely know some of the newest versions, you just have to go online and communicate with the PLC. Okay, so right here, I'm going to come over here and I'm going to select my CompactLogix. Now again, with this version here, I still have to down to the actual PLC, which is module 0 or slot 0. Okay, and then I'm just going to say go online at this point. I'm not going to upload or download. I'm just going to talk to the PLC. And you can see here now that this guy's actually currently running a program. Okay. And so it's actually asking me to select a file here. And so it's actually going to be uploading the file. Okay, even though I didn't select upload, I just said go online. The first time you connect, you have to really choose either upload or download. And since I didn't select either, it gave me the choice to either hit the download button there or to upload the file that it's currently running. And so then you can see what okay, but yeah, here's what I wanted to show you on this. They have, once you're online with version 20 here, you can actually say discover modules. And so this one will then go through there and scan the modules. Okay, it's not doing it at the moment, but usually it'll, maybe I probably have to be like in program mode or something, but it can actually go in and scan and identify the modules for you on the newer versions, which is kind of nice. All right, so I see some comments there, and actually I heard them ding. Normally I hear them ding here, but so yeah, when you're adding in the modules in the Rslogix 5000, right? Since you haven't actually talked to the PLC, you start a new program. It's not communicating with the PLC, so it doesn't know what modules the PLC has plugged into it. Okay, and so that's why we actually have to say new module and add. Right, but again, we can always flip over to the Rslogix, and the Rslogix is communicating with it, and it will show us what those modules are. Okay. All right, so let me flip back to the slides here. This was the slides for the ControlLogix, and I think I pretty much discussed everything that was in here. I'm just going to flip through here real quick. You can, take your time and review these again, but I'm just discussing the different things. So again, remember the electronic keying. You either have to set your revisions to match what the revision is on the actual card, or you can just kind of cheat and disable your electronic keying. Okay, so in the classroom, we just normally just disable it and don't worry about it. But the electronic keying is important when you set up faults. Okay, we don't do a whole lot of that in this class, but when you go look at, especially when you look at analog inputs and outputs, if you were to come in here and add if I was to come in here and add my analog module, okay, and this was slot 2, and I'm just, like I say, I'm just going to disable my keying here, and I'm going to select this, and they're warning you that, yeah, I don't know if you want to disable that. That's what they're saying here, okay? But of course, now, when you look at this, there's a lot of configuration going on in here. So one of the things that we don't really mess with too much in this class because of time, but the fact that when you create, and like I say, especially for analog modules, they actually have all kinds of built-in fault checking stuff. So your program can address, what happens if the voltage goes too high or the voltage goes too low, and you can set what a high or low means. Okay, so remember, like right now, channel 0 is set for a signal, an analog signal, to be between minus 10 volts to plus 10 volts. But we can say, you know what, if the sensor gets above 8 volts, I want you to spit out an error, an alarm. I want an alarm. I want to know. And so you can build that into your program. All right. And that's where this revision stuff, that's when we come back over here and look at the revision. That's when the revision is very, very important, because the alarms and things like that, maybe aren't supported in one revision or another, or they made a change. And the other thing is also you can do calibration. So you can do calibration things in here to make sure that it's calibrated to your sensors. And so, but again, a different revision of the card maybe is behaving a little bit different. And so that's where, you normally, if you're doing production, you really don't want to disable keying. You want to make sure that your revisions match and everything matches. All right, so now if we look at configuration, remember that we can configure this, and you notice there's 7 of these, okay, that's because I selected differential mode. So if you come back here, I selected differential mode, which means that it has the ground is when you do differential mode, it means that each channel has a separate ground. All right, and so you don't have to have, they don't all have to have the exact same ground in there. That's what differential mode basically means, is that you can have a different ground or a different zero value for each sensor that you wire up to this. All right, but when you do that, that costs you half of your inputs. So notice it's only showing 8 inputs. Okay, now I can count 7. It says 7 there, but remember we start counting at 0. So there's 8 inputs because I'm in differential mode. And then when we come over here, notice that we can choose. I talked about these last week, right? You can do voltage signal. Okay, so you can have a -10 to +10 voltage signal. You can have a 0 to 5 volt voltage signal. You can have a 0 to 10 volt voltage signal, or you can do a current input. Okay, and so you have to configure which one you're going to use, right? You have to select this. So when we were adding, like last semester in PLC1, when we were adding in relay cards or digital input cards, there wasn't really nothing to configure. Okay, but with the analog ones now, we have to decide, are we going to feed in a 10 volt signal, a -10 to +10 volt signal, or are we going to feed in a current signal? Okay, and we have to decide what signal we're feeding in, and then we got to come into this configuration and we have to set that. All right, now this is the ControlLogix, but if I go over and look at the CompactLogix, I get the same sort of thing. So if I come look at this configuration in the CompactLogix, okay, you not only have to choose what signal you're getting, but you actually have to click on enable. All right, and this is very common in the classroom. People are like, it's not working, and I'm like, pull up your configuration, and sure enough, you didn't even enable it. All right, so if you haven't enabled it, it's not going to work. Guess what? All right, so you have to enable it. Now the CompactLogix card, we actually have one analog card that has 4 analog inputs and 2 analog outputs, both in the same module. All right, so that's why when you read this, you see IF4, that means 4 inputs, and OF2 means 2 outputs. So it actually tells you that right in there. So if you want to use an output, you got to enable the output. If you want to use an input, you have to enable it, and you have to select whether it's going to be a voltage input or a current input. All right, so when we look at these modules, I'm just going to kind of go through the slides here. Okay. All right, so when we look at our modules, again, the ControlLogix are 1756s, and we can have 4, 7, 10, 13, or 17 slots in it. And a couple other things to note about these, okay? One of the things that are really cool about the ControlLogix, which you can't do with the CompactLogix, is these things are hot swappable. Okay, so I've jumped ahead here. I'm sorry, I know it's in here somewhere. They have forget the exact word they use, but it's like, or it's an acronym, removable under power. So it's like RU. Maybe it's in the other set of slides, but it's removable under power. It's like RUIP or something like that is the term that they use. Okay, maybe it's in the other set of slides. I don't know. I know I have it in the slides here somewhere. This RUIP, I believe, is the way it's spelled, but it means that you can remove it under power. Okay, so if the beauty about that is that if one of these I/O cards go bad, you can just pull out the card and plug in a new one. And so what's really nice about that, you see this here is a little plastic terminal strip. And so what happens, this terminal strip, this little gray piece is the door. You open up the door and it becomes a handle. And you pull this out and you pull this off, and then you can pull out the I/O module without shutting off power. So that means that you can plug in a new one. So you plug in the new module, push the terminal block back in, and you're back up and running, you know, in like way less than a minute. Okay, so if the module goes bad, you don't have to shut off anything. You just pop off this terminal strip, slip out the module, and pop in the new module, and then push it back. You don't have to disconnect any wires. You don't have to shut her off or anything. So it's really, really nice, you know, for replacing a module. Okay? So it has very minor interruption, you know, to the line. You don't have to shut down the line. You just pop that out. All right, so let's look at I/O modules here. So when we have a I/O module for analog cards, we have either analog to digital or digital to analog. All right, so we use the acronym ADC, which means analog to digital converter. Okay, so this would be the analog input card. And outputs are referred to as DACs, digital to analog converters. All right, so this is the circuitry for a 2-bit analog to digital card. And so what happens here, basically this uses these little converters, and you have these, or the comparators, I'm sorry, the little triangles are actually, technically they're operational amplifier circuits. They're little integrated circuits. And in this use, we're using them as what's called a comparator. So notice over here, I have a resistor divider network. All right, and this little resistor divider network, I have 4 resistors, and the 2 center ones, the 2 center resistors are 2K, and the outside ones are half of that, so they're 1K. And so what happens then is, if you look at right at the center, that would be 5 volts. And so you actually get this nice even divider. So if the voltage, if the input voltage, which is coming in here, if the input voltage is below 1.67 volts, or really it's 1.6666 volts, all right, and if that input voltage is below 1.7 volts, then I have 0. I have a 0, 0. If the input gets above 1.67 volts, then this goes high. This becomes a 1, which puts in a 1 over here. So I have a 0, 1. If the input voltage gets up to 3 volts, I still have a 0, 1. If the input voltage gets up to 4 volts, I still have 0, 1. If the input is 4.999999 volts, I still have a 0, 1 coming in as my input. So for this to go to 1, 0, or the value 2, decimal 2, it has to break the threshold of 5 volts. Okay, there's no rounding up in analog to digital converters. They do not round up. You have to break that threshold for it to go beyond that value. All right, so what that means, like in this example here, the highest voltage I can detect is 8.33 volts. Okay, if it was 8.32 volts, then I would think it's still at 5 volts. Okay, but this is only 2 bits. Okay, this is a 2-bit converter, and this is what the circuit looks like. And it has a resolution of 3.3 volts. So, you know, what that's saying is that I can detect when the voltage gets above 1.67 volts, then I'm going to detect that the voltage has changed. But now it's got to go another 3.3 volts before it's above 5 volts before I can detect that it changed again. All right. And then it's got to get up to 8.33 volts before I can detect that the voltage changed. Okay, so this is very, very poor resolution. All right, so this is a 2-bit converter, and I'm going to have 4 values. Okay, so I only have 4 possible values in here. The 4 possible values I have are 0, 0. I hate it when it gives me a white font. Like, really? Why would I want a white font? So I have 0, 0, which means that I'm at 0 volts. Okay. I have 0, 1, which means, well, the 0, 0 means I'm at somewhere between 0 volts up to 1.6665, oh shoot, 1.665, somewhere in there, volts. Okay, and then if I have 0, 1, that's telling me I'm at 1.66666 volts up to 4.999999 volts. And then if I have 0, 2, or excuse me, not 0, 2, if I have 1, 0 in binary, which is 2 in decimal, that tells me I have a voltage of 5.00 volts up to 8.3332 volts. And if I have 1, 1, that means I have a voltage anywhere from 8.33333 volts up to 10 volts, which is the maximum. Okay, so this particular analog to digital converter is a 10 volt converter. Okay, it doesn't do minus 10 to plus 10, it just does 0 to 10 volts. That's all this one will do. All right, but see, these are the values. So if I have 0, 0, then that's telling me that I've got a voltage somewhere between 0 to 1.66 whatever volts. Okay, so I'm below 1.6666666. Okay, If I have 0, 1, it tells me I'm at either 1.6666 all the way up to 4.999999. Okay. If I have 1, 0, it tells me I broke 5. I hit 5, that's the threshold. But I could have 6 volts, 7 volts, all the way up to 8.33332 volts. And if I'm at 1, 1, I'm up above 8.3333333. So I can only detect a change of 3.3 volts. Okay, 3.3 volts is the max. The voltage has to change beyond 3.3 volts before I can detect it. Okay. All right, so when you look at these are symmetric. These are built symmetrically. So, to go to a 4-bit, I could put in some more 2K resistors in there. All right, but that would change my resolution. So when you look at this, and I have a table set up in Blackboard that describe this. Let me flip over to Blackboard. All right, so if we go in Blackboard under Lessons, and then Analog Cards, I think it's under the outline here. Okay, so I tried to, yes, there it is. Okay, so if you have a 2 bits, you have 4 possible values, which means that your resolution is 3.3 volts. And so your first voltage is, oh, typo there, 6.666. If you have 4 bits, okay, so, and we're going from between 0 to 10 volts in this example, okay, so, and you can apply the same logic to a current signal, all right, but so if you have 4 bits, that means you got 16 possibilities, okay, which means that you can detect a voltage change of 0.6 volts. Okay. And the maximum voltage you could detect then, instead of being 8.3 volts for a 2-bit, you can detect a voltage of 9.67 volts. And so the first voltage you could detect would be 1/3 of a volt. All right, but you're going up by 2/3 of a volt. And so the next one you would detect would be 1 volt, and then 1.67 volts. Okay, technically that has, technically the 6 just goes on and on there. Okay, and then, but if you have an 8-bit, an 8-bit gives you 256 unique possibilities, which means you can detect 39.2 millivolts. So you can detect a change between 39.2 millivolts. And the maximum voltage then you would be able to detect is about 9.98 volts. Okay, so the first voltage you would detect was half of this. Notice the first voltage you can detect is half of the resolution. Okay, so the first voltage you can actually detect is 1/2 of the resolution, because the reason for that is if we look back at this circuit, here, okay, you see that the first resistor and the last resistor are 1/2 of the other resistor values in this little divider here. And that's why you can detect half of a, that's why the first voltage you detect is 1/2 of the actual resolution. So any questions about that? Okay, don't worry, I'll have lots on the quizzes and exams and things. So if you don't have any, that's great. Okay. They also make dedicated analog input modules for certain types of sensors. So they make specific, like for thermocouples, right? Thermocouples, we'll talk more detail about those later on, but thermocouples are used to measure temperatures. And so you can buy an analog input module that is designed to read just one specific type of thermocouple. But you know, you can read actually, you know, 6 or 10 of those, you know, so you can connect like, you know, 6 or 10 or 12 or however many thermocouples into that one analog input. You know, probably like, it's probably be, normally they're actually a multiple of 2. So 2 or 4 or 6 or 8, not 6, but 8 or 16 or something like that. Okay. But they're not always multiple of 2s, but all right. Okay, so this is just kind of showing some of those analog modules. Okay. All right, now when you wire these things up, okay, you can do either single-ended or differential-ended. And again, I kind of showed you that configuration when you have to know how you wire it up, obviously. And then when you wire it up, right, you tell it in your configuration right here how you wired it up. Did I wire it up in different mode, or did I wire it up single-ended? All right. So if you wire it up single-ended, then you get full use of all 16 channels, or how many inputs that you have. If you wire it up in differential, you're giving up half of your inputs, but you don't have to share a common ground. All right. And so I kind of show you in here, this was the IF16 input module. And you see all these different, it actually has 36 terminals connected to it. Okay, so you have 36 terminals to wire up if you're going to use all 16 inputs. And so this is just right out of the manual here, and they show you how to wire it up if you're doing single-ended mode or if you're doing differential mode. All right, and so the way you wire it changes depending on how you're using that. So you got to pay attention, read the manual. They're available online. You can download it and get that. But it makes a huge difference on how you wire it, whether you're using single-ended or differential. Okay, so if you're doing differential wiring here, notice you actually have to wire a jumper over here, because this is basically, it's a current. If you're wiring in a current, you got to have the current flow. So that's why you have this little jumper here running from current return, I return 0, has to then run over to IN1. Okay, but if you're doing a voltage wiring, the voltage wiring is on the right side here, and you don't have to have that return. Okay. So you have to know, are you actually wiring it up for a voltage input or a current input? And yeah, it makes a lot of sense that, right, if it's a current signal, you've got to give that current a place to return to. And so there's extra wiring for that. It's just like if you were trying to hook up a current meter. Okay, if you're hooking up a current meter to measure current in an electrical circuit, right, you would wire that in series. But if you're hooking up a current signal, or excuse me, if you want to hook up a voltmeter, you just hook that in parallel, right? So when you wire them up, whether you're doing current signals or voltage signals, it's a different wiring, just like with a DMM. You have to wire it differently for the different type of signal. All right, and so those are in here. You can review that, okay? The other piece is for output. So remember, the OF6CI is our output card that we have on our ControlLogix. And when you drive a load, okay, they have two different wirings depending on how much resistance is in your load. So if your load is 500 ohms or below, then you wire it up to these connections. But if your load is, this really should say 500 here. I need to save this and re-upload these set of slides here because I made a couple changes. If you're 501 ohms up to 1,000 ohms, then you wire it up to this alternate output. Okay. So you have to know what your load is, and of course you're going to have documentation on whatever your load is. If you're driving a relay or whatever, you need to know what the resistance of that relay is. Or actually, relays are digital. Sorry, yeah, relays are digital. This is analog. But whatever you're wiring up to, you need to know what its resistance is because you're outputting a current. This is the current module, right? The C means current. So you need to know how much resistance you're feeding. And it's a different wiring if it's above that. Now, when you output, we're outputting a digital value to a analog value. But what happens is you ended up, it only changes every scan. So remember the scan cycle of a PLC, they have scan cycles. And you only change the output once per scan cycle. So what happens actually is if you wanted to output a sine wave, here or something like this, the thing is that you're not going to be outputting all the time. So what happens is you're going to put in the output and then you got to wait for the next scan cycle before you output the new value. So you end up actually getting this kind of stair-step output, okay, because it's only going to change at the next scan. All right, and so that's due to the fact that, you're running through the code, you read the inputs. Remember what a scan is. You read the inputs, you execute the ladder logic, and then there's also some kind of system management stuff that's happening there, and then you send the outputs. And so you end up, instead of getting a nice smooth curve, you end up getting a stair-step sort of output, okay? Now, this is for a 16-bit output, so you can see the binary values changing there as we send the output. But if you had a 32-bit output and you had a faster thing, then it might be a little bit smoother. But you're still going to have a stepping sort of change at every scan. Okay, and it could be drastic. I mean, this is actually showing fairly nice, smooth steps, but in reality, your scan, maybe it decides that it's going to make a huge jump. And so the next one could be a huge jump and not a nice, smooth thing. In this case, I was trying to output a nice smooth sine wave, And so that's what I'm getting. All right, so I'm getting this relatively smooth stair-step action going on here. All right, this is just kind of an example of the resolution of your digital to analog output converter, whether it's a 2-bit or a 5-bit, 8-bit converter, and what those values would be. Okay, so just like we did with the analog. And this is what the circuitry looks like for a digital to analog output. So this is a 4-bit, this is a 4-bit output. And so when you notice this, I've got 4 switches or ones and zeros, right? So if it's 1, 1, 1, 1, that means all of these are closed, and I'm sending out my max output. But notice here, the most significant bit is 1K, and then the next one is 2K, 4K, and 8K. Well, if you remember, we were talking about binary, right? And we had that breakdown of binary, and we had those values where we had like, let's see, I was gonna, if we had like 128, again, it's white. Why does it default to white? Okay, so we had like 128, and then we had 64, and then we had 32, and then we had 16, and then we had 8, and then 4, and then 2, and then 1. All right, so notice the values of these resistances here. Okay, this is a 4-bit converter, so it's the first, it's 1, 2, 4, and 8. So if you were to have, if you wanted to make it a 5-bit converter, you would have to add a 16K ohm resistor down there with the next switch. And if you wanted a 6-bit, you would have to add a 32 kilo ohm resistor. And if you wanted to make it an 8-bit, you would have to add the 64 and the 128. Okay? And so the only thing you would be changing is you'd be adding another switch and then another resistor here. And the resistor values would just be this binary values going on here. So 1, 2, 4, 8, 16, 32. So if you had an 8-bit digital to analog, you would have resistor values broken down like this to generate that and hook it up to this operational amplifier here. Okay, and the other thing is R5 on this would have to be the highest value. So you notice here R5 is 8K, and so if you were going to make it a 8-bit, then R5 would have to be 128K. But this is what the circuitry would look like for an digital to analog. Okay. Now this one's real simple. We don't have the alarms and things built into it and stuff like that. So when you think about the like the ControlLogix one, right? And you look at that, remember they have like all kinds of alarm circuitry built in there and calibration circuitry. So there's a lot more going on in these modules that you would buy from Allen Bradley or Siemens or, you know, whoever built your PLC. There's a lot more going on than this little circuit here. Okay, but this is just a very simple one that you actually just kind of build yourself if you wanted. But this is what it could look like.